Finite element analysis of stress data in the cement of total hip prosthesis with elastomeric stress barriers. In the total hip prosthesis, according to different positions of the patient, there are a variety of loads acting on femoral head which generate stress concentration in the cement called polymethylmethacrylat, PMMA, and consequently it interfaces stem, cement, bone. In this work, a 3D finite element analysis was carried out to analyze two total hip prosthesis types, conventional model and redesigned model. In the second one, an elastomeric stress barrier of 0.5 mm thickness is incorporated between the stem and the femoral head in order to reduce the force transfer to the cement and consequently leads to minimized stress concentration.
In this study, we aim to treat carefully this process by using the design of experiment method. For each parameter, the effect of interaction with the rotation speed, the welding speed, and the choice of the pin were determined. A mathematical model between the response and the parameters are modeled, which represents the analytical part of these optimizations.
According to the motion situations, the forces in the three directions as well as their resultant are given in percentage according to the weight of the body of the patient, which is equal to 750 N.
The three factors of our matrix experiences are represented in this table.
Stress distribution in the cement body, PMMA, led to trajectories choice, external interface bone, cement ABCD, and internal interface stem, cement EFG as indicated.
We show the evolution of the rupture strength considered as a response influenced by the change of the three parameters, rotation speed, welding speed, and the tip of pin profile, amplitude from his low to the high level.
Von Mises stress distributions for the two models, conventional and proposed, are presented in the following figures according to the three loading conditions. The stress value level in the most concentrated area decreases by -42.5%.
The resistance is low for a square pin with high rotation and welding speed. We also observe that the resistance is modest for a large area.
The stress value level in the most concentrated area decreases by -42.0%.
The resistance is low for a square pin with high rotation and welding speed. We also observe that the resistance is modest for a large area.
The stress value level in the most concentrated area decreases by -42.4%.
The resistance is low for a square pin with high rotation and welding speed. We also observe that the resistance is modest for a large area.
In this finite element analysis of both conventional and elastomeric prosthesis, it was concluded that the obtained stresses in cement stem interface using the new proposed prosthesis with elastomeric material are generally lower than those found with a conventional model. Relative high stresses were observed at the cement stem interface of the conventional model with the three load types. The use of soft and flexible elastomer position between the stem and the femoral head with low rigidity is able to reduce the load transfer to cement. The maximum stress concentration has moved from the cement stem interface in the conventional model and reduced to the bone cement interface proposed model because of the static equilibrium of forces in the new system. The stress level reduction in the cement of the proposed prosthesis is estimated at 42%. In conclusion, the use of a shock-absorbing elastomeric material appears to play a key role in the charge of transfer mechanism in the cement response. This stress absorber reduces the stress on the cement and thus increases its service life, avoiding the loosening.
As a conclusion, the design of experiment technique was very confident for predicting the parametric design of input process parameters. The influence of the parameters is quantified. This process improves the quality of characteristics in terms of the first output response.